Hello, my name is David Gloria, and I am presenting my KIN 505 video presentation, CAP 1, ATP pathway for both glucose and palmitic acid. To the right is a diagram of the pathway ATP production for glucose, and you can follow that as I briefly go over some key points in this process. Let me move myself out of the way here. There we go. So let's go ahead and talk about the pathway ATP production for glucose. The first thing that happens is one molecule of glucose is split into two pyruvate molecules. Now, this process is called glycolysis, but this process also has 10 enzymatic reactions which go into it, which we're not going to go into much detail because of time, but it's important to note that glycolysis, the molecule of glucose being split into two molecules of pyruvate, is a 10 enzymatic process. Once the pyruvate is split into two molecules, we go into the transformation of pyruvate to acetyl CoA. And so as you can see, those two pyruvate molecules come down here and are now transformed, so to speak, into acetyl CoA before they enter the Krebs cycle or the citric acid cycle. At this point in the citric acid cycle, acetyl CoA is degraded to carbon dioxide and hydrogen atoms are carried via the electron transport chain. As we come down to this box, and the electron transport chain is where the actual ATP is formed, and when the hydrogen atoms oxidize in this phase. In each phase, a certain amount of ATP is yielded. So in the glycolysis step or phase, we have 7 ATP that we have yielded. In the pyruvate to acetyl CoA phase, 5 ATP has been yielded. And when we're in the citric acid cycle, a total of 20 ATP have been yielded for a net yield of 32 ATP. The diagram here shows 34 ATP yielded, but because two ATPs initially phosphorylate glucose, 32 ATP molecules equals the net ATP yield. So this is the pathway ATP production for glucose. Next, we have the ATP pathway ATP production for palmitic acid. And so just as the glucose breakdown, there's steps there. There are a few steps here as well. The first thing that we see is that a beta oxidation phase in which NADH and FADH2 are produced by splitting the palmitic acid molecule into two carbon fragments. So that palmitic acid molecule split into two carbon fragments, which then takes us to ATP phosphorylation. Here, water is added and hydrogen atoms past NAD and FAD. ACOL fragments join with coenzyme A to form acetyl CoA. So here we can kind of see that process happening here. The beta oxidation will continue until the entire fatty acid molecule degrades to acetyl CoA before it enters into the citric acid cycle. So once that molecule, that FFA molecule degrades completely, then it will enter the citric acid cycle in which oxidative phosphorylation begins. And this is where hydrogens are released during fatty acid catabolism and oxidized through the respiratory chain. And as you can see on the diagram, throughout this entire process, there is a certain number of ATP that is being yielded. And when we come to the end of that process, the complete oxidation of palmitic acid is 129 ATP. So these are the two pathways for ATP production for both glucose and palmitic acid. Some points to address how these pathways interact across exercise, intensity, and duration. A couple of things to note. During exercise at low intensity, fat accounts for most of the energy expenditure. As exercise intensity increases up to the lactate threshold, the contribution from fat decreases as the contribution from carbohydrates increases. This happens partly because the body now relies more on glycolysis to meet the greater demand or need for ATP regeneration. So when exercising just below that lactate threshold, the body is using mainly carbohydrates. And once the intensity of the exercise has risen above the lactate threshold, carbohydrates become the only fuel source for that intensity for as long as we are above that lactate threshold. Primary factors that might limit ATP production in each pathway. Let's talk about metabolites, because metabolites will either inhibit or activate at key control points in those oxidative pathways that modulate regulatory control of glycolysis and the citric acid cycle. Also, cellular ADP cellular ADP concentrates the greatest exertion and effect on limiting enzymes that control macronutrient energy metabolism. So metabolites, cellular ADP definitely plays a role and are factors that could limit ATP production in either pathway. And then finally, why can't we simply rely on the system that produces the most APT for all exercise? And I think, just a general kind of rounding out this presentation, it just brings things into perspective. The real world, sure, we've learned about it a bit, we've touched on some key points, but how does that relate to us, and what should we know moving forward as far as not only the processes of glucose and fatty acids, but also when those are used, how they're used, and as we go about our day-to-days, and especially during our times of activity or exercise. It's important to know that stored fat represents the body's most plentiful source of potential energy, and almost an unlimited energy. Between 60,000 and 100,000 kilocalories of fat is distributed throughout the entire body. However, the power generated solely by fat breakdown represents only about 1/2 that achieved with carbohydrates as the chief aerobic energy source. A common question that I get from time to time is, if more energy is derived from the breaking down of fat compared to that of carbohydrates, then why doesn't the body go after or prefer to oxidize carbohydrates? And really, the short answer to that is the rate of release, the energy released, is just of fat is too slow and less readily available than that of carbohydrates. And that's because fat has to be reduced from its most complex form, which is a triglyceride, into its most simple form, which is glycerol or free fatty acid, because only free fatty acids can be used to form APT. And because that process is much slower because of the additional steps that fat has to go to produce ATP, the body chooses to use carbohydrates as its chief energy source. Also, fat metabolism requires a constant supply of oxygen, and overall the delivery of energy is just slower than that provided by carbohydrate metabolism. However, fat will and can become the primary energy for fuel for exercise in recovery when intense and long duration exercises deplete our glycogen levels. So you think of a marathon runner, think of a triathlete, think of people who can train consecutively long periods of time, inadequate energy intake, food intake, a depletion of carbohydrates or a very low carb diet. diabetes, all these things play a role and are factors in why our glycogen levels will and can be depleted, and why fat would become the chief fuel source. Now, it's not always a good thing when fat becomes our chief fuel source, but it's important to know why those things are happening. And the last thing is that just to kind of piggyback is depleting muscle glycogen decreases a muscle's maximum aerobic power input. So again, that is not a good thing either. Depletion of glycogen depresses aerobic exercise intensity, and it reduces carbohydrate availability limits for energy transfer capacity. So hopefully we've learned a few things here today. The processes, the breakdowns of glucose and free fatty acids, and hopefully we've also learned what's taking place in the body, how fats are used, how carbohydrates are used, when it's a good thing, when it's not a good thing, and hopefully moving forward we'll continue to learn more. So thank you for your time. I will see you soon.